Hi, and welcome to MSc. In this video, we're going to be looking at the discriminant. So the discriminant is the part of the quadratic equation under the radical. It's the radicand. It's the part underneath the square root symbol, and it sometimes goes by its own variable, capital delta, which is a triangle, the Greek letter delta. And so it's a very important piece of the quadratic equation because it tells us how many roots we will expect to find for that quadratic, how many x-intercepts. So if the discriminant, the b squared minus 4ac, is greater than 0, then there'll be two x-intercepts. There's two distinct real roots. So as an example, I've drawn out a couple of them here for you. You can see both of these quadratics, these parabolas, have two roots, and I've labeled them for you there. This was done up in Desmos. Let's look at the second example here. I'll leave the other one as an exercise on your own if you're interested, to show that the discriminant of g at x, which is this curve here, has a discriminant that's greater than 0. So we're going to say, okay, well, b squared minus 4ac, well, b was the 10, so 10 squared minus 4, and the a is -1, and the c is -18. Okay, again, I put brackets around these because I'm subbing in a negative. I could easily put brackets here around the 10 as well. That would be especially important if the b value was negative. So this will be 100 minus, and let's break this up. So -4 times -1, well, that's just +4. And then we still have the -18. 4 times 18 is going to give me 72. And it's going to be negative, so -72, and then this equals 28. And we can see that, yes, the discriminant was greater than 0, and that's why it's not surprising that we have two real distinct roots. They're different from one another, right? And you can repeat for the f at x function. There's no c value, and you can take a look at what that does. But any parabola that has two real roots will have a discriminant that's greater than 0. So if you're asked how many roots it will have, you can jump straight to the discriminant. The next scenario is, well, what if it was less than 0? So if it's less than 0, then there's no x-intercept, right? And you've seen parabolas like this before. It's been vertically translated up or down so that it doesn't cross the x-axis at all. There's no real roots. But actually, there are, in fact, two distinct imaginary roots. Let me explain. So here we have, again, two of these drawn up for you for comparison's sakes. Let's take a look at one of these to show you what I mean by it being less than 0, and then I'll dig into it more with the imaginary root piece. Let's try the h at x for this example, and you can repeat it for the j at x function there if you'd like. So we're looking at b squared minus 4ac, and for the b value, I'm putting in my 2, minus 4, a is 1, c is 4, and this will be 4 minus 4 times 1 is 4 times 4 is 16, and we'll get -12. So certainly the discriminant is less than 0. I'm not going to have any real roots, and sure enough, the parabola does not ever intersect the x-axis. How does that lead then to imaginary roots? Well, you may have heard about the fact that if you had the square root of -1, that we actually just call that I. So let's take a look at the quadratic formula very quickly for this and try to figure out what the intercepts are. And we know that there's no real ones, but we're going to get two complex numbers come out of this. So the quadratic formula is -b plus or minus the square root of 4ac, which is our discriminant, all over 2a. And I know you probably have that memorized. It's often given to you in formula booklets as well. So let's sub in what we know here really quickly. So it's -2 because of the 2 from here. And we already now know that we're dealing with plus or minus the square root of -12 all over 2a. And so this is 2 times 1, and there it is. So this is going to be -2 plus or minus the square root of, and I'm going to write 12, and then I'm also going to multiply that by the root -1 all over 2. So this will become -2 plus or minus, and I can actually simplify that 12 I can say that's going to be root 4, root 3, and instead of the root -1, I'll say I. All of that is over 2. And I've run out of space. I'm going to bring that back up here. And we're going to say that x can be equal to -2 plus or minus square root of 4 is 2, root 3 over 2, and then I can simplify and say x, oh, and there's an I, almost forgot that, and this would be -1 plus or minus root 3i. So we call these imaginary roots. This is a complex number. It has a real piece and an imaginary piece. And these are the imaginary roots. And notice that there's 2 of them because there's the plus scenario and the negative scenario. So depending on how comfortable you are with imaginary numbers, that part might have made more or less sense to you depending on where you are with your math curriculum. But when we talk about having no real roots, it is important to remember there's actually 2 imaginary ones. It's kind of cool. Last scenario then is when they're equal to 0. When the discriminant is 0, then that means there's one x-intercept. And actually it kind of means there's 2 identical real roots. And so here's again a few examples. I'll do one, you can try the other one out on your own. And so let's look at this first one, the m at x function. And so we have our discriminant, and I'm subbing in. So the b is -12 squared minus 4a, and c is 18. Okay, so this will be positive 144 minus 8 times 18. All right, well, 8 times 10 is 80. 8 times 8 is 64. 80 plus 64 is 144. So no surprise, we get 0, and that's why we only have the one root that we have. So how is this actually like 2 identical real roots? Well, when we work through the quadratic formula, and if you bear with me, I'll do this really quickly for you. When we sub into the quadratic formula, we're going to end up with a plus or minus in it still. And we often can just kind of ignore the fact that there's 2 roots. But let's sub in here. So b was the negative of the 12, and this we know is going to be plus or minus root 0, and then it's going to be all over the 2 times 2. And I won't take this any further at this point. You can finish this off, but we can see how we get a plus and minus a 0 scenario, which leads to the same value twice. So we say that there's physically one intercept, but there's actually 2 identical real roots. And so it's splitting hairs a bit, but you can really picture that quadratics will always have 2 roots. 2 distinct real roots, 2 imaginary roots, or 2 identical real roots. But we can determine that not having to work through the entire quadratic formula, but by looking to the discriminant, which can go by the delta symbol, and looking at, is it greater than 0? That means that there's 2 distinct real roots. They're different from one another. If it's less than 0, then the parabola never crosses the x-axis on the real plane, and you're using the real numbers. And so there's 2 imaginary roots, and if the discriminant is equal to 0, then we know that there's one x-intercept, or 2 identical real roots. And so we can solve that or answer how many roots we'd expect very quickly without having to go through the entire quadratic formula. I hope this short run through has been helpful on what the discriminant is and why it might be useful. Thank you very much for listening and watching.